Let us now look at the most important aspect of branch prediction, where arguably the maximum amount of research work has gone in, which is predicting the outcome of the branch. So this is the most difficult problem. The rest of the problems are relatively easier to deal with, easier to manage and handle. Right? We already have created an IST for predicting the instruction type. What we have further promised is that we will somehow merge the IST with the structure for predicting the branch target. But let's go sequentially step by step. So once we know that an instruction is a branch, next we need to figure out whether it's taken or not taken. So here also we assume a black box. The black box, the program counter comes in, and what comes out is whether it's taken or not taken. Say the branch is unconditional, then it is always taken, so there is nothing to predict. If a branch is a call or return, it is also taken all the time, so here also there is nothing to predict. The fun comes in conditional branches, like branch if equal, branch if not equal, which are essentially dependent on the outcome of the last compare instruction in the program. So the compare instruction, essentially what it does is that it sets a set of flags. These flags record the outcome of the compare instruction, whether it led to an equality, inequality, greater than, less than, etc. And these flags are subsequently used by later branch instructions like branch if equal or branch if greater than and so on. So they see what the comparison resulted in, and based on that they are either they go in one direction or the other. So not taken is of course the sequential direction PC, PC plus 4 and so on, that is not taken. Or they can go in another direction which is taken, where we jump to the branch target. So let us consider a piece of example code. We'll show the C code and we'll show the simple RISC assembly code. So the simple RISC assembly, the simple RISC language, assembly language is appendix A of the book, and it has also been discussed in previous slide sets, and it is definitely there in the videos of the previous book. So this is a two-part book. In the first part of the book, the simple RISC assembly language has been described in great detail. So let us look at the for loop, which goes from 0 to 5. So what we do is that we treat R0 as the loop variable. We initialize it to 0. So then we compare it with 5. If it is equal to 5, then of course we exit the loop. This is our termination condition. Otherwise, in every iteration of the loop, we increment the loop variable by 1, which we are doing over here, and again we loop back. So this is the loop. All right. So the jump is essentially a backward jump. So this is the loop, and as you can see, we are implementing the for loop almost identically in assembly, where we initialize, we check the exit condition, and we increment. So normally whenever we implement a for loop, we follow these 3 steps of initializing the loop variable, checking for termination, and incrementing. So we see that we have one conditional branch which is BEQ, and this needs to be predicted. So the branch, if we look at it, it has roughly similar behavior most of the time. So most of the time it is not taken, because the condition that makes it taken does not happen. So that is only when R0 will be equal to 5, and that will happen very rarely towards the end of the at the end of the for loop. So note that we are assuming a dot exit label, which is the end of the program. So this is not shown. So now, given that we have seen this pattern, that this branch by and large is not taken, it's only taken in the last iteration. Can we use this pattern? Well, yes. So what we do is we create a predictor that is extremely similar to the IST that we had designed in the previous lecture, where we predicted the type of the instruction. So here what we do is we take the n least significant bits over here, all right, and the n least significant bits that we have, we use it to index address a 2 to the power n entry table. All right, we were doing the same in IST. This is exactly the same logic. So what we do is, akin to the IST, we remember the last outcome. So we can say that not taken is represented with bit 0, taken is represented with bit 1. So we simply store 1 bit over here where we remember the last outcome and the outcome of the branch. So whatever was the last outcome, we say that look, the current predicted outcome is also the same. Say the last outcome was not taken, we say that look, this time also we predict that the branch is not taken, and likewise is the case for taken. This is a very simple predictor. So let's evaluate and let's see if it works or not. So what we see is that the BEQ instruction is evaluated 6 times. So let us go back. So here if we see this iteration, it actually runs 5 times, and the 6th time we actually find out that we have reached the end of the for loop. So this statement is evaluated 6 times, 5 times for a genuine iteration and the 6th time to exit the for loop. Out of these 6 times, the first 5 times we correctly predict not taken, if we assume that we start from the not taken state. But the 6th and the last time we also predict not taken, which is wrong, because in this case the branch is taken. So this is what we should have predicted it to be. All right. So now let us assume that the function foo contained this loop. So if it contained this loop, what will happen if we keep on calling the function foo is that, so let's say we call it the first time. So the predictions will be not taken 5 times. So let's write that. The last time the branch is taken, so we'll make a mistake. The next time we come to function foo, we will still predict that the branch is taken, right? So the next time that we come, let me write it over here. We will predict that the branch is taken. Why? Because the last time we encountered the branch was taken, so we will make the same prediction. This will be a mistake. We will realize it was not taken, so next time we'll predict it's not taken. We'll keep on doing it for the next 4 times. Again we will predict not taken, which is the last iteration of the for loop. This is again a mistake. So this is the function foo. If we call function foo once again, we will repeat the same pattern. So what we will actually see is that our misprediction rate is as high as 2 by 6 or 1 by 3. So recall our discussion in chapter 2 where we discussed that the accuracy of a branch predictor should be very high, 96, 97, 98% at least. But here we see that the accuracy is very low. In fact, the accuracy over here is only 66.66%, which is way lower than what we actually need. But that's fine. This is the first predictor that we are seeing. And this predictor, as we can see, has a built-in flaw. And the built-in flaw is that it always predicts whatever was the outcome the last time, which in this case appears to be a bad idea. So we make 2 mistakes, one while entering the loop and one while exiting the loop. So let us see where is the problem. The problem is that the BEQ branch if equal instruction is fundamentally biased towards the not taken direction. There is one exception at the end of the for loop, right? So but the point is that the single exception at the end of the for loop cannot change, should not change its inherent behavior, right? So what is the inherent behavior of the branch? The inherent behavior is that the branch is predominantly not taken. It is just in the last iteration of the for loop in which the branch is taken. However, this should not, one exception should not change the way we perceive the branch. So we need to add some degree of prior history or some degree of hysteresis to the branch. So instead of having a single bit in each entry, let us have a 2-bit counter, which to a certain extent can have this history or some degree of hysteresis, such that the inherent behavior of the branch will get recorded, right? It will not change, it will get recorded. So let us add what is called a saturating counter. So a saturating counter is a 2-bit counter, where if a branch is taken, we keep on incrementing it. The reason it is called saturating is because when it reaches its maximum value, which is 1, 1, at that point of time it does not increase anymore, it is not incremented anymore, and the value remains over there. Similarly, when the branch is not taken, we decrement the value of the counter. When it reaches 0, 0, it is not decremented further. It remains at 0, 0, right? So its value is not decremented further. So this is why the counter is set to saturate at both the maximum value and the minimum value. So this is where the counter is set to saturate at both the maximum as well as the minimum values. And whenever, as I said, when we increment, we go in this direction, and when we decrement, we go in this direction. So how and when and why are saturating counters useful? Well, when the state is 0, 0 and 0, 1, this is when we predict not taken. And if you can see, whenever a branch is not taken, we keep decrementing the counters. That is why when the state reaches 0, 0 and 0, 1, which is close to, which you will reach when you have been decrementing the counter, so we predict not taken. And similarly for the two upper states 1, 0 and 1, 1, we predict taken. So what is the algorithm again? Well, if the branch is taken, we increment it. So ultimately, if the inherent behavior of a branch is such that it is taken all the time, it will saturate at this stage and will predict taken. Just in case we make a single mistake once in a while, we'll still move to this state. So it allows a single anomaly. So in this case, we will still continue to predict taken. The same is the case with not taken as well, where if a branch is predominantly not taken, most of the time the state will remain at 0, 0. Let's assume that there is one odd anomaly such as the one at the end of the for loop. So in this case, the state will be 0, 1. However, we'll still predict not taken. The main reason being that we need to make two such mistakes. I mean two such taken branches, and that too consecutively are required to pretty much change the behavior of the branch. So given that we have seen this pattern, let us give the names to the states. So let 0, 0 be strongly not taken, which is this state. 0, 1, let it be weakly not taken, which basically means that if let's say the branch is taken once, it will move to stage 1, 0, and then we will start predicting taken from that point onwards. Let 1, 0 be called weakly taken, which is named in a similar manner to weakly not taken. And finally, let the state 1, 1 be strongly taken, which has the same connotation as strongly not taken. And once a state is at strongly taken, if let's say it's not taken just once, it will still come to this stage, which is fine, we'll still predict taken. So a saturating counter is very code, it works very well when a branch is biased, in the sense when a branch predominantly takes one direction with one odd anomalies sometimes. So let us now create a branch predictor with saturating counters. So we shall take a regular bimodal predictor. Everything remains the same. We use the bottom n bits to index a 2 to the power n entry array. So in this case, instead of having a single bit in each entry, it has a 2-bit saturating counter, right? So instead of having a single bit or one bit in each entry, it has a 2-bit saturating counter over here. So then if let's say we want to predict, we read the value of the saturating counter and we pass it through a logic block. What this does is that it basically looks at the MSB of the saturating counter. If it is 0, we predict not taken. If it is 1, we predict taken. So this is the predictor table as you can see over here, which broadly remains the same. When we find the outcome of a branch, we again access this entry, and if it is taken, of course we increment. If it is not taken, we decrement. But the logic is the same for the saturating counter, in the sense if the state is already 1 1, we don't increment it further, it remains there. So the saturating counter is very useful. Let's see why. So let us take a look at the same piece of code again. So in this case, the first 5 times we predict correctly, which is not taken. The 6th time, of course, we make a mistake, so we predict taken. But the state after this is actually weakly not taken. And so the next time that we enter the first branch, we will still predict not taken, primarily because the state is at weakly not taken, which means that from the saturating counter logic, even if we make one mistake, the inherent behavior doesn't change. So in this case, the inherent behavior still remains not taken, and that is why we don't make the mistake over here that we were making with the regular bimodal predictor. So this mistake does not happen. That is why the mistake rate here is 1 over 6, which if we compare it with 2 over 6, it's roughly half, it's 50% better. So as we can see, we have been able to bring down the mistake rate substantially, and now it is only 1/6, which is roughly 16%. What was the key trick, the key innovation that we used? Well, the key innovation that we used is that the mistake that we were making over here, primarily because the exit iteration was taken, and we continue to predict the same with a bimodal predictor. In this case, we don't do that, mainly because we created an additional state called weakly not taken, and this records the steady state behavior or the long-term behavior or inherent behavior of the branch. All right, so as you can see, we remain at 0 0. In this case, because the state is taken, we move to 0 1. The next time we start with 0 1, we move to 0 0. So even if we were to execute these 5 iterations with 6 branches over and over and over again, we will still see that our error will saturate and stabilize at 1/6. So the misprediction rate, so let me erase the ink on this slide. So the misprediction rate has gone down from 2/6 to 1/6, which in a certain sense represents a substantial improvement. Now, why do saturating counters work? Well, as we have discussed, they introduce a degree of hysteresis. They introduce a degree of in a sense, they incorporate the inherent behaviors of the branches. So in this case, the BQ exit instruction moves between the strongly not taken and weakly not taken states. So when does this work? Well, when a branch is strongly biased towards one direction, but once in a while changes its direction, that is when we use saturating counters. They capture stable behavior with occasional anomalies. So of course, a bimodal predictor captures stable behavior, but if I were to include occasional anomalies, I would have a saturating counter based predictor. Can we do better? Well, let us consider a slightly more complicated piece of code, and let us look at if we can do better or not. So let us take a look at this piece of code, which has 5 iterations. So in the last iteration, which is if I is equal to 4, then we call some other function which is foobar, right? So this function is called. Let us look at the assembly code over here. So in this case, what we do is, where the first few lines are the same, we move 0 to R0, we compare R0 with 5. If the comparison results in an equality, we exit, we go out of the loop. Otherwise, we execute this comparison if I is equal to 4, we compare R0 with 4. If the comparison is not successful, which will happen most of the time, we jump over here, we increment R0 by 1 and we loop back. The interesting case happens in the last iteration when we compare R0 with 4 and the comparison results in an equality, which means that we call the function foobar, and then after calling the function again we return and we increment the loop index, which is R0, and go back to the loop. So in this case, we still confine our attention to this branch and we try to reduce the error to 0%. How do we do that? Well, we have a solution. So let us introduce a new structure called a global history register, or a GHR. So let this be a shift register that records the history of the last n branches encountered by the processor. Alright. So in a dynamic instruction sequence, if this is the current point, I look back at the last n branches regardless of the program counter, and for the last n branches, I store their status and I store their outcome, and the outcome can either be taken or not taken, taken or not taken. Right? So if I have a single bit for each, alright. So if I have a single bit for each and I represent taken with 1 and I represent not taken with 0, then at any point I'll have an n bit vector where it will record the history of the last n branches in the dynamic instruction sequence. So if I consider a 2-bit shift register and call it the global history register, then the shift register is also known as the GHR. So the GHR in this case contains 2 bits in our example, which means it records the history of the last 2 branches. So recall that we have 2 conditional branches in the running example. So of course we can modify the GHR logic to only record the behavior of conditional branches. So that will give us more accuracy, as we shall see. So let us assume we do that. So we have 2 conditional branches in our running example, and at every point of time we maintain the status of the last 2 branch instructions regardless of their program counter. So let us call this the GHR. So what is the status of the GHR? So at the beginning of the second iteration, the last branch over here would have been taken. right? And the one before that would have been not taken. So the status that we would record is 0 and 1, 0, 1. Even at the beginning of the fourth iteration, it would be 0, 1, right? Even at the beginning of the fifth and last iteration, also it will be 0, 1. However, at the beginning of the sixth iteration, the status will be different. Why? Because let us see what happens in the fifth iteration. This branch is not taken. There is an equality over here, hence this branch is also not taken. As a result, when I reach the beginning of the sixth iteration, which is this point, and I take a look at my GHR for the status of the last two branches, which would essentially be this branch and this branch in the previous iteration, the status would be 0, 0. Right? So in this case, we can think of the GHR as somehow encoding the context of a branch in terms of the outcomes of the n previous branches in the dynamic instruction sequence. So in this case, as we see, at any point we can of course inspect the GHR. So the beginning of the iterations, second to fifth, the GHRs are all 0, 1, 0, 1, 0, 1, 0, 1. But at the beginning of the sixth iteration, if we take a look at the outcomes of the last two branches, which would be basically the outcomes of the branches in the fifth iteration, their status is 0 and 0. So the GHR would contain 0, 0. So since it contains 0, 0, recall that the GHR values at other points was different, right? It was 0, 1, 0, 1. So in this case, it is 0, 0. Can we use this information to predict the BEQ.exit branch better? Well, yes, we can, and we will see how. So you can clearly see a difference. You can see that in the other iterations, the state of the GHR was 0, 1, but in the crucial sixth iteration, when we exit the loop, the state of the GHR is 0, 0, and this information is different, it is unique, and it can be used. So what do? Well, we make a gap predictor. So we'll mention why it is called a gap predictor in some time. But essentially what we do, what our idea is that we take n bits from the PC and we consider a k bit GHR. So in this case, of course, in our example, k is equal to 2. So what we do is we concatenate n and 2. So in this case, we create a n plus 2 bit field. This is used to address a table of 2 raised to the power n plus k entries. So now this table does not have 2 raised to the power n entries, but it has 2 raised to the power n plus k entries. So in this case, what are we doing? We are essentially combining the information of the GHR and the PC, which means that for a single PC, of course, not considering aliasing, for different GHR values, we'll have different saturating counters. If it's a 2-bit GHR value, we'll actually have 4 saturating counters instead of 1 associated with the PC. And for a given GHR value, of course, the saturating counter will record the behavior of the branch, the steady state behavior of the branch, right? Not the steady state, but in a saturating counter sense, it will record the behavior of the branch. So what are the two values that we see most common? 0, 1 and 0, 0. So most of the time it will be 0, 1. With 0, 1 we can store not taken. So in any case, in the process of training, this is what the saturating counters will get trained to. But if we consider 0, 0, what we see over here is that in no other iteration is the value at this point for BEQ equal to 0, 0. And furthermore, when the GHR is 0, 0, the branch is always taken. Hence, what we can record over here, which automatically the saturating counters will get trained to, is actually 0, 0, and at this point the branch is taken. So what we see from this is there is a nice way to differentiate the cases, the previous cases when the branch is not taken versus the case in which the branch is taken, and this can be used for better prediction as we see right here. So what did we do? Well, we created 2 to the power k times more entries in the predictor table. We had to do that because we considered a GHR, we captured the global branch history. We use both the global history as well as the local per PC history to make the prediction. Right? So we actually use both the global history as well as the local history. So how do we do that? Well, because we are combining both pieces of information, we are taking n bits from the program counter and we are taking k bits from the global history. So this is a total of 2 to the power n plus k entries. So which basically means that per PC we have 2 to the power k. Per PC we have 2 raised to the power k saturating counters. So each one of them is determining the behavior of the PC with respect to a given context. So the accuracy in this case is expected to increase, and as we can see in this case the branch in the last iteration will be predicted correctly. So in general we can create different combinations of the PC bits in the GHR's branch history. So it's important for me to look at this issue once again. So as you can see in the last iteration the branch over here is different, the GHR is different, it is going to be hence in no other iteration do we see such a pattern, hence the branch will be predicted correctly. There is one point that we need to mention which we have not written over here, but let me complete this. This is the beginning of the first iteration. So in the beginning of the first iteration essentially we are entering this function. So wherever we are entering this function from, uh, essentially the context of the last two branches will come from there. So if it is 0 0, of course we'll predict taken, which is a mistake, but the odds are that it will not be 0 0, right? I mean if we assume it varies uniformly, right, even if it doesn't, uh, it will not be 0 0 all the time. I mean statistically, we need to take our chances. So if it is any other value 0 1 1 0 and 1 1, so in these cases of course the context is different. So if it is 0 1 we'll predict not taken. If it is 1 0 and 1 1, then the saturating counter will automatically train itself to predict not taken. The only difficult scenario can arise if, let's say, when we enter the function foo, the existing context is 0 0, then automatically we are already trained ourselves to predict taken over here. So we'll predict taken and we will make a mistake here. But as I said, there are 4 states, so the odds are more likely that we would have 1 0, 1 1, 1 0 or 0 1 as the starting state of the GHR. So in this case, we can the saturating counter will automatically be trained to predict not taken. All right. So, but we will revisit this issue later, because the point is that if the first iteration the state is one of these, then it is clear that we are not making any mistake for BEQ.exit. So the error rate is 0%, right? So effectively we have a 100% accurate branch predictor. But in the beginning of the first iteration, if the context, the state of the GHR is 0 0, then of course there is a problem, because for the same PC and GHR combination, sometimes we will predict taken, which is this case, but when we enter the loop we want to predict not taken. So how do we exactly capture this context, right, and how do we exactly address this issue? This will be discussed a few slides later, but it is important to keep this thing in mind. So let us proceed. So what we have seen is that we have created a new kind of predictor, and the predictor is not just limited to predicting the 6th iteration correctly, which we just did, but let us assume we have a branch that has an alternating pattern, taken, not taken, taken, not taken. So it is clear that a saturating counter will not capture this pattern, right? Because saturating counters are designed to capture steady state behavior. But this behavior needs to be captured. So the question is, will a gap predictor capture this pattern? Well, the answer has to be seen by looking at the design of the gap predictor. So the gap predictor is essentially combining n bits of PC information, and it is concatenating this with k bits of the GHR. So the GHR is kind of unique. It has a unique signature for taken, it has a unique signature for non-taken. Then of course a gap predictor will capture the pattern. But this need not be the case all the time, right? So there need not be a very unique signature for this, because after all the GHR is not taking the PCs into account, right? So essentially it is the last k branches in the dynamic instruction sequence, which can be any set of program counters. So in this case, having a unique signature for taken and not taken might not be possible all the time. So we need to design some other predictor that can capture such alternating patterns and also solve the problem that we discussed regarding the first iteration of the loop, right? So both of these have to be captured somehow. So we need a better way of capturing them. So to design a better way of capturing such patterns, so what are the two patterns that we are still not been able to capture? Well, the first is an alternating pattern, which is taken, not taken, right? So this can happen, particularly if we have random numbers in the code. This can happen. The other is the first iteration of our running example. So then of course the context is coming from instructions that are outside the function, and we pretty much don't know, and the context is not under our control. So basically in that case also, if the context, as we have discussed, if it is not taken, then of course it's possible to predict the branch with 100% accuracy. But if the context is taken, then there is a difficulty. So if I were to look at both of these problems, I would need a branch predictor which is more complicated than gap. So what I do is I start with creating a design space of predictors where I call them GAG, GAP, PAG and PAP, and we will see that they have an they capture different patterns in the code, and these patterns uh, are commonly visible patterns in the code, and only if they are captured will we get a high accuracy. So at this point it is important to mention what is G and what is P. Well, what is G? If I were to come back to this slide, so G is the global history register. So G is the global information of the behavior of the last k branches in a dynamic instruction sequence. This is the G. And essentially the pattern is something that takes PC bits. So it takes these PC bits. So in this case, the reason we call it gap is because we have the global history, of course, and then we take these PC bits, we concatenate them, and we address a table. So this table is also known as the PHT or the pattern history table. And from this table we get a single saturating counter as output. And with this we can determine the outcome of the branch. Furthermore, to reduce aliasing, as we have discussed, we can store a part of the tag within each entry, but that is independent to this discussion. But the reason, as you can see, it is gap is because this is the G part and the PC, this is the P part. So similarly, we can have a hierarchy, a design space of other kinds of predictors, which hopefully will capture these two patterns, the alternating pattern and predicting the first iteration of our running example with a greater accuracy. So let us consider the most simple GAG predictor, which of course is not practical, it is not used. but it is a bona fide member of our branch predictor design space. So in this case, we don't use PC bits at all. So there is no P, as you can see. So we have a single K bit GHR. We only use the global history to access a table with to the power K entries, where each entry contains a saturating counter. And this determines the outcome of the branch. So this, of course, is not a good idea because we are not using the PC information at all. So there is no per branch information that is stored, which of course is not the right thing to do. To solve many of our problems, we will use the PAG predictor, PAG predictor. So this predictor is designed differently. So it is meant to solve both the problems that we have been discussing. So instead of one GHR, we have multiple K-bit GHRs. So what we do is we extract N1 bits from the PC address. So I've deliberately offset N1. I have not kept them as the LSB bits, but I have kept them somewhere in the middle. So what you need to do is that if N1 is 3, we will have 2 to the power 3, 8 of these GHRs. Each GHR will store K bits. So what we do is that we use these 3 bits of the PC, address the corresponding GHR, extract K bits from it. Furthermore, these K bits are used to index and entry the PHD of 2 to the power K entries, the history table with 2 raised to the power K entries, and each of these entries contains a saturating counter. All right. So what is the advantage of having multiple GHRs as opposed to a single GHR? Well, the advantage of having multiple GHRs is like this, that consider a very large program. So typically what happens is that we operate in the vicinity of one set of functions. So maybe let's say we are initializing the program. So this would be one piece of code. Then let's say that we are executing some logic, it will be another piece of code. So consider this PowerPoint presentation. So when I started PowerPoint, the initialization code was there. Then I was making the presentations, another piece of code was being used. And then I'm giving the presentations, another piece of code is being used. So all of these pieces of code are in a sense co-located in terms of addresses, right? They are located in similar addresses. So we should ideally have separate GHRs for these because we don't want the GHRs of, we don't want a single GHR, it does not capture the context very well. But for each code region, we would like to have a separate GHR, such as the context in that code region, which is more relevant, is captured. So what we do is, that's the reason we don't use the LSB bits, but we also don't use the MSB bits because they might remain constant. But we extract N1 bits from somewhere in the middle of the PC. So this, of course, where and which bits we extract, this is dependent on many simulation studies, so it is hard to predict. But ideally, it should not be the least significant bits because this is defeating the purpose of having multiple GHRs. So we typically have multiple GHRs when we want each GHR to capture the behavior of a certain region of the code. All right, so that is typically the reason why we have multiple GHRs. So we need to bear in mind that if N1, if let's say we extract N1 bits as the least significant bits of the PC, and let's assume that N1 is, let's say, 8. So what will actually happen is that we will pretty much be tracking 256 contiguous locations, and each GHR will capture the context of the instructions whose lowest 8 bits match. So in general, there is no meaning for the context of instructions whose lowest 8 bits match, because there is no relationship between them typically. But if, let's say, the program is kind of constrained within these 256 instructions, then the GHR can pretty much provide the context of the single instruction of let's say one instruction. It can kind of provide its past history. But this anyway we don't require, because we have other ways of recording, as we have seen, histories of a single instruction. So GHR pretty much captures the behavior of other related branches, right? So the philosophy of having a GHR is to capture the behavior of related branches. So what makes a branch related? Well, one way that we can actually define it is that we can say that, look, all the branches that are within a certain address range are kind of related to each other, because they are pretty much maybe part of the same function or part of the same super function that calls the sub functions, right? So in that case, it does make sense to offset n1 a little bit, such that if, let's say, n1 is offset by 4 bits, so then pretty much we are capturing a region of 16 bytes, and any instruction within that region, they are pretty much sharing the GHR entry. There are numerous trade-offs in designing this, but pretty much the idea of a GHR is to capture the context of the current branch and co-located branch and other branches that are in the same address region. Once we have done that, the context is used to address the table of saturating counters. So as we see, this is not, all that beneficial. Well, the reason being that we are only capturing global history, albeit global history of a given range, but we are not using the PC bits directly. So the PAP predictor pretty much combines everything that we have seen up till now. So it uses n PC bits directly. In addition, it has 2 raised to the power n1 GHRs, where essentially we capture the behavior of other branches, right, in the region, and we also take into account the last n bits of the PC. So what we do is we concatenate them. So concatenating them basically means that for a given PC, we have 2 raised to power k entries in the pattern history table, right? And so then we can pretty much capture different kinds of global history patterns. For different kinds of global history patterns, we can store different saturating counters. So the PAP predictor is clearly the largest of all 4, and it is also the most expressive predictor. There is another way of combining the information. So as you can see in the PAP predictor, we have 2 raised to power n plus k entries. There is another way of combining this information. What we can do is that we can take a k-bit GHR, of course it's a single GHR, and we can take n bits of the PC and we can XOR them. So XORing them is basically one way of kind of mangling the bits. So in that, what happens is this somehow mixes. So this is actually an extension of the gap idea or the gap predictor, where the gap predictor would do the same, but it would concatenate. In a G-shared predictor, what we do is, instead of concatenating, we compute an XOR, exclusive OR of the bits, which whose conceptual aim is to pretty much achieve the same of combining the PC and GHR information, albeit using much less space. So that is the reason the number of entries that we have here is 2 raised to the power max n comma k entries. That is the total number of entries that we have here. And each of these entries has a saturating counter, which, of course, we have seen a lot of saturating counters by now. All of them operate in the same fashion. So let us go back to the PAP predictor over here and first clean the ink on the slide. So let us see if it solves our problems or not. So let us first consider the first issue that we had highlighted, which was to take care of iteration 1. So in iteration 1, our line of argument was that look, the foo function starts. We have some instructions and then we have beq.exit. So we do not know the context of the foo function in the sense what were the branches before we entered the foo function, because they determine the global history. Alright. And since they determine the global history, we were not sure because there are different functions that could be calling foo. And given the fact that different functions are calling it, they could have different behaviors. So for example, it is possible that one function foo bar would be calling foo, that would have a different context, and another function foo would be calling foo, that would have a different context. So capturing the context in this sense is in a sense important. And also the other thing is that maybe, you see, if they have different contexts, then it's fine, that will get captured by a single GHR. But it is possible that they would have the same GHR patterns, right? And then there would be some degree of uh, aliasing, in the sense what we have seen is that if, let's say, the last two branches are not taken and not taken, essentially 0 0, we could predict the sixth iteration correctly. Now it is possible that the context from which the foo function was being called, we are having a similar GHR with 0 and 0. So in this case, we know that the first beq.exit, that is not taken, but we see in a similar context it is actually taken. So to solve such kind of issues, it is important to actually have multiple GHRs, which is exactly what a PAP predictor has. It has multiple GHRs. So in this case, if foo bar is calling foo, we would use one GHR. We would use one GHR for all the branches that are within the foo bar function. But once it enters the foo function, we would enter a different region, and this region would have a separate GHR of its own. So this separate GHR of its own would capture the context of all the branches that are only within the foo function and adjoining addresses, right? So what we are saying is that if we have multiple GHRs, then all the branches within the foo bar function, which will be in the same region, will have one GHR for it, which will be a separate GHR. All the branches in the foo bar function, given that they will be co-located, will have a separate GHR for them. And all the branches within the foo function, which are all co-located in terms of addresses, will have a separate GHR. For predicting the first branch, the branch that we are interested in, beq.exit, we will essentially use GHR3, which is the GHR of the foo function, and this would kind of be unaffected by the behavior in other regions of the code. So what would this be populated with? This would be populated with the information of the branches the last time the foo function ran, and managing this is far easier. So the last time that foo function ran, we deterministically know what were the values of the branches, the outcomes, the values of the outcomes of the branches, and that would accurately, uniquely, precisely determine the context, and this context can be used to predict. So let us give an example. Let us go back to our loop example, where we essentially had two branch instructions, beq.exit. So I'll take you there for reminding you. So we had two branch instructions, beq.exit and bne.inc. So what happened is that in this branch of the sixth iteration, we exited. So what were the two branches before it? Well, so this was one, So this one was taken, and the one before it, which was BNE dot inc, so this one was not taken. So given the right, so basically given the specific convention that we are following, what the GHR would contain in this case would be the contents of this instruction first. Sorry, the contents of this one first, which is 0, and the contents of this one, which is 0, 1. So which means that if I'm able to dedicate a GHR for the foo function, the next time that we come to this branch, we are going to see the value of the GHR as 0, 1, and given the fact that 0, 1 always corresponds to not taken, we will predict correctly. So what have we effectively done with the PAP predictor? What we have done is that for every region of code, we have broadly associated a GHR with it. This ensures that this GHR is not polluted with the GHRs by the behavior of branches in other regions. And this further means that let's say we exit function foo, go to other functions, do whatever we want. The moment we come back in, we will pretty much use the GHR associated with this region, which will capture the behavior of what happened last time. And so this, at least in this case, is a more accurate predictor of the branches. So let us now consider the second pattern, which was an alternating pattern. So the alternating pattern, let's say for a given branch, so let's say the pattern is taken, not taken, taken, not taken, and in between an arbitrary amount of code can be executed. So what we really want in this case is, we want to, in this case, we are interested in the last outcome of the current branch, right? And based on the last outcome of the current branch, we make a prediction, right? So the last outcome was 1, we say it was 0. If the last outcome was 0, we say it is 1. So this is ideally not possible in a saturating counter based system. The reason being that the saturating counter will always predict. So saturating counter is more for a very biased branch, but in this case, it is an absolutely 50-50, alternating unbiased branch. So a saturating counter will not really work, because the moment it sees 0, it will try to predict 0, but you are trying to do the reverse. So you would need a global history in this case, and the global history should be confined to this PC. It should not be polluted with other global histories. That is why we need multiple GHR registers. Now if you want to predict it, well, all that we will do is we'll take n bits from the PC, and let us consider a single bit GHR, which is the last outcome. So we will essentially have two entries, n0 and n1. So n0, even if we have a saturating counter, it doesn't matter, n0 is always 1. So of course 0 is not taken, 1 is taken, and n1 is always 0. So these two values will ultimately saturate, and the PAP predictor will be able to learn this alternating pattern perfectly. So what we see is that some of the major issues that we had with a traditional bimodal saturating counter or gap predictor, the PAP predictor is able to fix most of them rather well. And one reason for this is that it is able to capture certain patterns rather very well, which other predictors could not. One of them is this alternating pattern. The other one is the first iteration of the foo function, which should ideally depend upon what is it, should ideally depend upon only the context of the foo function and nothing else. So having multiple GHRs helps us avoid that destructive interference. Now, given that we have seen so many predictors, what we have seen is that for a biased branch, for a highly biased branch, we would need a predictor based on saturating counters. For something that is heavily dependent on the context, like an alternating pattern, we would need a PAP predictor, a PAP-like predictor that has multiple GHRs, and there is a lot of context, right? So here I actually stand corrected. For an alternating pattern, actually a gap, instead of a gap, a PAP predictor works very well. So the question is that for a given piece of code, how do we know which predictor to use? Because for a highly biased region, we should ideally use a saturating counter based prediction because it will work best. Because we can always use a PAP predictor, but larger is the predictor, the longer it will take to train, and more are the resources, more are the overheads. So in this case, what we should ideally do is that for different regions of the code, depending upon their behavior, we should use different predictors. So maybe for one region of the code, the gap predictor is the best. For another region of the code, it's possible that the PAP predictor is the best. Maybe for another region of the code, the G-shared predictor is the best, right? Because they have different behaviors, and for these different behaviors, different kinds of predictors actually work well. So what we need is that for a given code region, which means for a given PC, we need to choose which predictor to use, right? So we'll have multiple predictors and choose one of them. So what we do is that we define a tournament predictor, which given the PC, we extract n bits. We have a choice array. So in the choice array, again we have a saturating counter. So the saturating counter essentially tells us which predictor to use. If it is 0, we use this predictor. If it's 1, we use this predictor. And based on the predictor to use, we use its prediction, and that's the final prediction. So the advantage of this is that for different program counters, we get to know what is the best predictor that we can use or what works best. And this also gets trained in exactly the same way as a regular branch predictor. And this also captures the history information to a large extent of, given a range of code, what to use. So the operation of a tournament predictor is as follows. We find the entry in the pattern table first. Then we choose the predictor based on the value of the saturating counter. So what do we have? I'm sorry, let's not call it the pattern table, let's call it the choice array. Right, the pattern table is for an intra predictor table. So let's call it the choice array. So what happens is that if we have the program counter, we extract n bits out of it and choose an entry in the choice array. So here we'll find a saturating counter C. And there are two sub predictors, pred1 and pred2. So if pred2 is correct, what we do is we increment it. And of course, this is incremented in a saturating counter fashion. Similarly, if pred1 is correct, what we do is we decrement it. So ultimately, what will happen is that for a given program counter, one of the predictors will most likely be found to be suitable. So the saturating counter will go and saturate over there, and we'll use it. Of course, later on, if the behavior changes, then the saturating counter will also embody that fact. So based on the value of this counter, we choose the predictor. Then the predictor, we give it the PC and all information that it needs. It provides a prediction, and that is the final prediction of the tournament predictor, right? So for training, what do we do? Well, for training, we train both the predictors with the PC and the ideal outcome. We train the entry in the choice array if we choose the wrong predictor. So let's say that, we chose pred1, but actually pred2 was correct. Then of course we train the entry in the choice array. If both the predictions are the same, then of course nothing needs to be done. If they differ, what we do is, if predictor 1 was correct, then we change the saturating counter. So let's say we increment the counter, and if it was incorrect, we decrement the counter. right? So it doesn't matter, as long as we stick with one convention, that let's say if predictor 1 is correct, we keep on incrementing, predictor 2 is correct and predictor 1 is wrong, we keep on decrementing, or vice versa, it doesn't matter, as long as the same convention is followed. So what we see over here is that for different code regions, different predictors are known to work well, and the tournament predictor essentially has all of these predictors as sub predictors, and for a given code region, it just historically, based on historical knowledge, it chooses the most accurate predictor. What are some other methods of prediction? Well, to reduce aliasing, we can incorporate a few tag bits. For different kinds of branches, subsets of branches, we can have multiple predictors. This can either be decided dynamically, as in the tournament predictor, or it can be decided statically, which means the compiler can say that, look, for this region use this predictor, for this region use this predictor. We can include a bias bit with every branch, which maybe the compiler can find out, which is its most likely direction, and just predict if we agree with the bias bit or not. What many other modern branch predictors do is that they separate branches into high confidence and low confidence. So we use different bits for different kinds of predictors. So for high confidence branches, we use predictors with few bits. But with low confidence branches, for low confidence branches, we use predictors with more bits. Because of course the bit budget is important, right? We have a finite amount of area on the chip and we don't want to increase it substantially. The examples of few more predictors are bimode, agree, skew, YAG, stage. So stage of course is known to be a very accurate predictor, and nowadays many predictors are kind of inspired by very early stage neural networks like perceptrons. So you can also look at perceptron based predictors. So these predictors are known to have a extremely high accuracy, and the way that they work is that they divide branches into different subsets and they use different methods to handle each subset. So one of the famous predictors is a skewed branch predictor, where it takes all the information, address, bits, global history, and it has different functions to kind of mangle the bits and means compute different combinations of the bits, and for each of these combinations we use one predictor, right? So this is kind of a conceptual extension of G-share. And let's say if we use three predictors, we use the majority decision. If two say not taken, one says taken, we use taken as the prediction, the majority decision. Is there a theoretical analysis of branch prediction? Well, yes. So if you take an information theory course, what you will find is that prediction and compression and compressibility of the sequence, they are very related. So let us do one thing, consider a sequence of PC and outcome pairs. Let us compress this sequence using a standard program such as zip or rar. So let's say the size of the original file, which just had the PC and outcome pairs, was 100 KB, and after compression it becomes 20 KB. So the compression ratio is 5. Is the prediction accuracy related to this ratio? Well, yes. How? There is something called the Fano's inequality that relates both. So what the Fano's inequality basically says is that for a given trace of branches, which means for a given program that has a certain behavior, and the behavior can basically be in a sense quantified with just creating a trace of the PC and branch outcome pairs. If we have this, there is a theoretically maximum prediction accuracy, right? So there is a maximum theoretical prediction accuracy that is related to the compressibility of the sequence and the mathematical result that stands for this relation is the Fano's inequality. So this is the maximum theoretical prediction accuracy. This can be given by the Fano's inequality. So information theory has a concept called entropy, which is very closely related to the compressibility of a sequence. And the Fano's inequality uses that to put a bound on the maximum prediction accuracy, which means that regardless of whatever you do, we simply do not have enough information in the sequence to have a higher prediction accuracy. Alright, so we have looked at predicting the branch outcome, which is arguably the most complex part of this design. The next is prediction of the branch target. This is easy. So we are the PC of the taken branch, we need to find the target. Well, all that we do is that we augment the IST, which is something that we had promised in the last video that we are going to do. So we augment the IST. Recall that the IST was a single 2 to the power n entry table where we use the last n bits of the PC and it gives us the type of the instruction. In this case, we store the target over there. So we store the type of the instruction and the target. And for additional, we can also store a tag for taking care of aliasing related issues. And of course, we can also store the target. So the BTB, which is essentially extending the IST, solves two purposes, which is it solves problem 1. Problem 1 was the type of the branch. And it solves problem 2. Sorry, it solves problem 3, which was finding the target. So along with the type of the branch, we also stored its target. And anytime we see a branch, we record its target over here. Alright? Such that we access the BTB and we get both the type of the instruction, if it's a branch, what kind of branch, and also its target. Because for unconditional branches, the outcome need not be predicted, but the target has to be predicted. So the BTB in that sense is a very important structure. And modern processors actually have a 2-level BTB. They have a level 1 BTB, which stores the most frequent program counters. And then it has a level 2 BTB, which stores slightly infrequently observed program counters. So together, so the L1 structure is small and fast, and the L2 structure is slow. So given that now we have solved all three of our problems, which is finding the type of the branch, predicting the outcome, taken or not taken, and finding the target, let us look at the other branch types. So unconditional branches, of course, nothing much needs to be done. We just need to find the target and that's it. But calls and returns are interesting. So consider a function foo. So the function foo calls foo bar. So this is the return address. Foo bar calls foo bar bar. This is the return address. And foo bar bar calls foo bar bar bar. Right? So then again we return. So once we return to this return address once again. So how do we predict these return addresses? Well, we can use a regular BTB mechanism. That can be done. Because after all, to predict, so call is also an unconditional branch. And to predict the starting address of this function, which is essentially the branch target of the call, we will use a BTB. Right? So why not do it for ret? Well, we have a far more accurate solution. So just take a look at this pattern. So if you look at this pattern, it is a last in, first out kind of pattern, in the sense that foo bar 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 was last in, but it was first out. This was second last in and second last out. So anytime we see a last in fast out pattern, we use the stack data structure. The stack data structure is nothing but just like a stack of books. we stack the functions. So first we stack foo, then we stack foo bar, then we stack foo bar bar, then we stack foo bar bar bar. Whenever we return, all that we need to do is we need to pop out. So we stack means what? We stack the return address. So whenever we return from, let's say, foo bar bar, we just pop out the function, and uh, we basically, that is the return address, and the return address is supplied to the pipeline. So how would the stack look like? Well, we have a description in the next slide. So let us say that foo calls foo bar, and the return address is 0xfc0. So fc0 is put in the stack, right? Sorry, this is a horizontal stack, sorry. Now let's say foo bar calls foo bar bar. So in this case, 0xff4 will be put in the stack, which is the return address for the foo bar bar function. Then again, let's say there's one more function called. So then the return address is again put in the stack. Now once we return, what we do, right? So take a look at that again. Once we return, all that we need to do is we need to pop the stack. The top entry of the stack corresponds to where we need to return to, which is essentially this address. We pop it. Let's say we want to return again, then we pop it once again. And now let's say from here we call some other function. Well, no problem. We push in the return address once again. Alright. And that's not an issue. But let's say that this function returns again. Then essentially the last return address is popped. And now our return address stack is empty. Alright. So in this way, instead of using a BTB which is kind of inaccurate, we have a far more accurate solution of actually operating the function calls and returns. All that we need to do is we need to have a small stack in hardware that simply just stacks the return addresses as we just saw. So let me replay the animation for you. So foo calls foo bar, we store the return address once again, and whenever we return, we just pop the stack, and the top entry of the stack is where we need to return to once again. Alright, so this is as simple as maintaining a stack in hardware. So now let us summarize the entire branch prediction system. So the branch prediction system, the BTB, is a key structure in the entire system. It has an extremely important role to play. So what the BTB does is that for every PC, for certain bits of the PC, it stores the type of the instruction. If it's a branch, what kind of branch, and so on. Additionally, it also stores the branch target. So the type and target are given. So the BTB is also used by unconditional instructions like call instructions. Then we have a return address stack, which is used by RET instructions. So the moment we call a function, so if let's say function A calls function B and B calls C and so on, their addresses are put into a stack. When we return, since we will be traversing the reverse route, we keep on popping entries from the stack. Dealing with conditional branches is the most difficult, so that is the reason why our second problem was to find the direction of a branch, or rather the outcome of a branch. So predicting taken or not taken is hard, but we looked at a lot of designs and we were able to capture many patterns with our designs. So the basic fetch logic would consist of these three modules, and they will help us choose the next program counter. Of course, now there are augmentations to this to perform many branch predictions in parallel, such that we can choose the next PC or the next 2 PCs or next 3 PCs or next 4 PCs. Now we'll come to the last part of this lecture, which is describing the decode stage. So this will be a rather short lecture.